Okay, so we're looking at a solution for number 31 from section 8.2. And in this case, it's important to note that we can take the function that's given and then use the power rule to find successive derivatives, first and second derivative, and then we're going to do something with that to answer the questions. So the first question they ask us is using derivatives to find the critical points. So I'm going to find the critical points of f and then the critical points of f prime, which means I have to find the first derivative and then the second derivative. So using that first derivative, I'm going to try and figure out where this first derivative is either equal to 0 or where this first derivative is undefined. Current form in the two-term kind of a form here doesn't really help me much, so I'm going to factor that. I can factor 5/3 out of both terms. I can also factor x to the negative 1/3 out of both terms. You have to, when you deal with fractional exponents, a lot of times it's this algebraic trick of factoring out the smaller of the fractional exponents. If you see what happens here, x raised to the negative 1/3 multiplied by x to the positive 1 gets us this x to the 2/3. And then x times x raised to the negative 1/3 times 2 will get us this term over here. So using that factored form, it's easy to see that the first derivative is 0 when x is negative 2. I think take this fractional exponent, it's a negative fractional exponent, and rewrite that as a positive exponent using cube roots. It's going to be in the denominator, so this entire derivative is undefined when x is 0, or when this cube root of x is 0. So that's when x is 0. So I have those two pieces of information. I can also do something with the second derivative. So likewise, we'll factor out 10/9, and then we'll factor out x to the negative 4/3. And when we do that, kind of working backwards here, x to the negative 4/3 multiplied by x to the first power, that will get us this x to the negative 1/3. And then we can do the same thing to get the second term. So rewriting x to the negative 4/3 as a positive exponent in the denominator, you wind up with the cube root of x to the 4th, which is 0 when x is 0. So f double prime of x is undefined when x is 0, and f double prime of x is 0 when x is 1. So we have those two pieces of information. Let's put those on our line graphs. So let's work with this blue equation up here first. And note a couple of things. So when x is more than 2, more than 0, we'll have a positive something multiplied by a positive something. So these will be positive first derivatives. When x is between negative 2 and 0, the second factor will be 0, negative, and the first factor will also be negative. Okay, I said that wrong. This is going to be the first factor will be negative, and the second factor will be positive. So we'll have negative values here. And then if x is less than negative 2, the first factor is negative, and the second factor is negative, resulting in a positive first derivative. So these things go up, and then down, and then up. You can see that in the graph over here too. You can see where the maximum and the minimum actually occur. So looking at the second derivative and kind of the same sort of analysis here, this time let's choose values of x that are less than 0. So that first factor, well, that's going to be positive. Next to anything to the 4th power is going to be positive, so this is all positive. And then if x is less than 0, this second factor is negative, so we have negative second derivatives here. In between 0 and 1, we'll still have negative second derivatives. This will still be a positive factor multiplied by a negative factor. It isn't until we get values of x larger than 1 that we wind up with positive second derivatives. So in terms of the shape of our graph, we wind up with a concave down graph. So first it's increasing, then decreasing. So the graph looks like that. Increasing, then decreasing, but concave down both times. then the graph is increasing after x equals 0, but it's concave down first, and then it's concave up. So we can see the point of inflection there. So to answer the third question, we've got a point of inflection at x equals 1. To answer the second question, to explain why there's a tangent line, you really do need to look at the limits. So we'd have to say the limit as x approaches 0 from the left of f prime of x. We want to look at that first derivative. So let's actually examine this guy over here. Let's get rid of that square that we have. So when we're examining this and thinking about choosing values of x that are really close to 0 but negative, we'll have a negative factor, pretty large negative factor because you're dividing by something that's really tiny, but it's negative. And then a really small negative number plus 2 is going to be positive. So this is going to be some large negative value. So this approaches negative infinity. And then if we think about choosing values of x that are approaching 0 from the right-hand side, so these are all small positive values of 0, again thinking about this, the first factor will be a positive value, and we're choosing values of x that are really close to x equals 0. So we've got a positive value, and then a small positive number plus 2 is also positive. So this is tending towards infinity. And you're like, well, wait, those are different. But when you think about this in terms of the slope, this just means that f of x has a really big negative slope and then a really big positive slope. Those are vertical lines. So the tangent line at x equals 0 is just a vertical line. And that's all they're trying to point out here. Okay, well, I hope that helps for number 31, and I guess I'll see you in class on Monday.